Afternoon or morning to you, depending on the time zone you're in. I'm Nathan Ham, Vice President at SCS, and responsible for leading our Leachate treatment and industrial wastewater management practice. I'd like to again welcome everyone. Thank you for joining our webinar. I know we all are busy, have lots vying for our time, so we appreciate you deciding to dedicate this hour to us here. We hope you come away a little more knowledgeable about the science of pipe scale formation and some takeaways of kind of how you can attack that and some of your operational challenges there. I know anyone really who's managed a landfill has likely experienced some form of pipe clogging or resulting challenge at some point during their career. It's a pretty common problem in our experience and only seems to be increasing in frequency and also in the difficulty of managing. Those problems can be both persistent and frustrating. We've assembled a pretty good group here, I think, of SCS technical experts on this subject today. Our group includes scientific and engineering perspectives from within the office and also some boots on the ground field perspective. Our first speaker today is going to be Sam Cook. He's a professional chemical engineer and SCS's Director of Leachate and Wastewater Treatment. Sam will be kind of taking us through a brief scientific primer on scale formation mechanisms. Following that, Mark Lefebvre, also a chemical engineer, will be giving us some experiences on a facility with a very aggressive inorganic scale problem and some of the techniques that have been pilot tested at that facility to manage the situation. Mark Pearson, also professional engineer, more than 4 decades of wastewater treatment experience, will be going through our black goo organic scale, which is the one I think a lot of people are very interested in and seems to be something that's definitely becoming more common and problematic, across the country. And he's also going to talk about some of the alternative treatments available at that type of scale. Final panelist is Mr. Brian Kelly. Brian's our senior site superintendent. He'll be providing kind of the boots on the ground perspective. He's got a lot of years in the field at the landfills, dealing with all kinds of scale problems, and can provide this perspective of really kind of how it goes versus the engineering perspective and scientific perspective. So that, again, as Diane mentioned, we'd like to keep this webinar very interactive. Encourage you to chat in your questions through the Q&A portion there. I will try to get those questions answered. If not, we will try to get back to you towards the end with a response at some point there. And with that, I'm going to turn it over to Sam Cook to kick off our discussion.
All right, well, thank you, Nathan, and really appreciate everyone taking the time to attend this session. So when we talk about pluggage versus relatively clear pipes, wells and pumps, etc., it's really all about the conditions that exist where the deposits occur or don't occur, hopefully not, right? Whatever those conditions are, though, your wastewater is chemically always trying to achieve equilibrium. You're familiar with deposits occurring in some pipes, wells and pumps, etc., and not in others, which pretty much we all are familiar with that. Then you know that there's different conditions that exist between where deposits are occurring and when they're not. So let's just take a fairly simple example at the start here. Think of conditions that exist in a water heater supplied with well water. Well water is being heated. You can have higher concentrations of minerals, your typical calcium, magnesium, iron, etc. Mineral deposits will tend to occur, but not usually any organic deposits in the water heater, right? That's because solubility of calcium decreases with increased temperature. There isn't usually a carbon source in the well water. So part of talking about conditions needed for deposition to occur is a calculation called the Langelier saturation index, or we call it LSI, which uses wastewater data and can predict if hard scale deposits can occur. And wastewater conditions listed in the first 5 bullets here on the slide are most of what makes up the Langelier saturation index. The next few slides will go into some more detail regarding this. So let's assume that the leachate or wastewater that you're managing has some of the conditions that can exist to promote deposits occurring in the pipes and wells and pumps. So based on what we know, based on research, wastewater like landfill leachate has some added components that further promote the deposits forming. Sticky stuff like man-made polymers that can be in landfill leachates and also landfill gas condensates, as well as polymer producing organisms are often associated with black goo deposits that Mark will be talking about. We know that microbiological growth naturally produces polysaccharides. Want to also point out that landfill leachate and other wastewaters often have ingredients that form inorganic deposits. So we've talked about the calcium carbonate deposits in the water heater, but it can also be something called struvite. That's the magnesium ammonium phosphate. And all of those constituents, the magnesium, the ammonium, the phosphate, are all typically found in landfill leachate, and under the right conditions, and by right conditions, I'm talking about really the wrong conditions, since we don't want deposition to occur, include all three of those constituents that, by the way, form in an equal molar ratio, 1 to 1 to 1. But calcium carbonate and struvite aren't the only inorganic compounds that can be a problem, because there's also iron and other inorganic compounds that also form deposits. So with the right conditions and constituent concentrations, that leachate condensate is essentially like a deposition soup. Not only that, and continues to get worse because conditions can coexist for organic and inorganic deposits that can create even more complex forms of deposition. And colleagues will be talking about that. So let's get into some of the specifics. Here you see wastewater treatment plant sludge after it's been dewatered. In this picture, you can see the sludge coming off the end of the screw conveyor. So I bring up sludge because we find that landfills that accept sludge tend to have more black goo deposition in their pipes and pumps and wells. And during the sludge dewatering process, polymers, like what you see in the slide there, can be used, or the sludge has the polymers that can be used to hold the sludge particles together and promote the separation of the solids and the liquids. And it's thought that when this type of sludge is put in a landfill, then potentials exist for those polymers to get into the landfill leachate. And even at relatively low concentrations that you'd expect to find in a leachate, they're thought to become part of the black goo. And if you haven't had the opportunity to see this type of sludge firsthand, it's moist and tends to be naturally sticky.
Say I'm kind of going back and talking about, these wastewater polymers and stuff that's there, with the challenges that people are having with emerging contaminants, specifically talking about PFAS, a lot of times those biosolids from wastewater treatment plants have historically been land applied, for beneficial use, as a disposal method. But with, pending regulations, some states already enacting regulations, others in the process of getting that done and looking at what the federal government might do, it seems that more and more of those materials are going to be coming to the landfills potentially for disposal, creating, further exacerbating that problem. In your experience, do you need to be taking large amounts of for example, wastewater biosolids to have issues with this, or can even just smaller quantities create problems with your leachate?
Yeah, smaller quantities can definitely. I mean, the more that you have, then the more chance that you're going to get those polymers in your leachate. But even at fairly low concentrations, the polymers and of course the polysaccharides that we're going to be talking about next, those tend to build up. And again, you have this, it's all about that equilibrium and about the chemistry of your leachate and the conditions that exist in the pipe. And so you can have a very low, relatively low concentration of one, but you have other factors that make it so that the black goo in organic case or the inorganic deposits can build up. Again, it's all about conditions, and just a little bit of sludge can exacerbate that. So, good question. So along the lines of, we talked about, it gets worse or getting worse. Another sticky organic deposit can occur are polysaccharides that we just talked about. Naturally forming organic substances excreted by microorganisms, the bugs, and that sticky excretion helps the bugs to stay in place and form colonies. The bugs naturally want to kind of stay put if they're in the right conditions. So those polysaccharides are sort of the glue that hold them to the community or the colony where they want to be. And so those excreted polysaccharides are long chains of the same type of molecules you see here. Imagine long strings of saccharide molecules that you see, and when excreted by the trillions of microbes, it could be living, eating, reproducing, and the pipes, pumps, and wells where the organic deposits form, then you can just imagine how over time, the right conditions, there can be a lot of buildup of organic materials. And so we've been talking about organic deposits. On this slide, you can see what some typical inorganic deposits look like from the side. So these are cross-cut pipes to show how deposits form, very often in layers, because different deposition conditions can exist. Going back to that whole issue of conditions in the pipe. So sometimes deposits are more homogeneous than what's shown here, and there aren't layers, but this shows different deposits of calcium carbonate and other inorganic constituents that under different conditions have deposited in layers on the inside of the pipe. So like tree rings, you can see the three left images show force main deposition with more equal thickness of the deposition around the pipe, the inside of the pipe. And the right-hand image shows more of a gravity flow pipeline pluggage. So deposits are more located at the bottom of the pipe. To give you a little bit more insight into how these deposits form, when conditions in the wastewater pipe are right for deposition, here's an image that shows the evolution of the buildup of pipe deposition. So graphic with the orange-brown materials, the macro detail of what's occurring over time on the more micro level of the pipe in the background. So what this shows is how the clean pipe, shown on the left of the blow-up detail, becomes closed off with more and more over some period of time. Sometimes it can be relatively short, sometimes longer, and you'll hear more in the case studies. But as you move to the right, with, in this case, the orange and brown combination of organic and inorganic deposits, you see it being built up. And at the far right, you can see that the deposits have built up so much, they're even breaking off and moving down in the pipe with the flow to possibly deposit in other locations. So we talked about the LSI, the Langelier saturation index previously, and here's the actual equation. And LSI is a good indicator of whether or not your wastewater has a tendency to scale, be neutral or be corrosive, around calcium carbonate. But instead of using this equation, there's much simpler calculators that you can get free online. And to use the simpler LSI calculators, you need to have some data from sampling of leachate or wastewater in question. And that would be like pH, the calcium concentration, alkalinity concentration, temperature, and the total dissolved solids concentration. So the simpler online calculators have you input that data, and through the use of factors that you see here in that more simple equation, right below the more complex equation, you can get the LSI value. And an LSI of between negative 0.3 and positive 0.3 is considered neutral or balanced water, which means that it tends to not scale and not be corrosive. Greater than positive 0.3 is considered scale forming. So that's to the right. And it can go much higher than the 0.5 that's shown there. And less than 0.3, negative 0.3, is considered corrosive. Bottom line from all this is the higher the LSI, if you use that calculator, the worse the calcium carbonate scaling problem will likely be.
Sam, I think it's important to point out that that's really only for, that calcium carbonate scale formation, the inorganic scale, right, not for the biological or like the black goo type stuff that, we'll be talking about later in the presentation.
Exactly. Very good.
All right. Thanks, Sam. Appreciate that's kind of our scientific primer, if you will, of scale formation mechanisms. And that, I think, a really good lead into a couple of case studies that are going to come up here. So I'm going to turn it over to Mark Lefevre, who's going to talk about a very challenging inorganic scale site.
Thanks, Nathan, and everybody for joining us today. Much appreciated. We're going to discuss a case study for a facility located in the Southeast US. It's about 291 acres and is a former unlined municipal landfill. It's also a former Superfund site listed in 1983 and delisted in the late 1990s. After some groundwater remediation and additional assessment work with the EPA determined that the site posed a low risk to human health. There was some remaining risk to aquatic species and wetlands. The site is currently about 200 acres as mixed-use development. Constituents of concern are ammonia and chlorides. SCS has been involved in the site for about 10 years, and my involvement is over the last 3 years or so. We face a number of challenges at this site. There are 32 independently operated extraction wells to recover ammonia in the leachate impacted groundwater, but drawdown in the wells must be controlled so as to not exacerbate chloride concentrations in sensitive wetland areas. SCS must maintain these wells to operate 24/7, 365 days a year with minimal downtime. Several years ago, scale deposits began to appear and have progressively worsened, causing some of these wells to be inoperable for extended or even indefinite periods of time. Standard practice in many landfills is to conduct acid cleaning and jetting to remove scale deposits. We have performed this periodically at the site, but the scale comes back very quickly and is difficult to perform due to small diameter piping and few cleanouts.
So Mark, looking at your picture there, you say things coming back quickly. That picture in the upper right-hand corner, maybe there's an inch or a quarter inch or something of flow path still left in there. How long at this site did it take typically to achieve that kind of a pipe occlusion?
Yeah, I mean, we have one area where we've conducted some pilot tests. We have about 450 feet or so of pipe that's actually above ground. It's actually hose that we installed. And that took about 30 days to plug that solid to that extent. In the lower left-hand corner of the slide, there's a foot valve. We also have some surface-mounted extraction pumps that we use. And that particular foot valve took less than a week for it to scale to that degree. On the right is a submersible pump. That's the motor that's coated in scale. And I wanted to point out too that, some of these color variations are also due to slight changes in the chemistry of the calcium carbonate. It could have additional iron present, it could have sulfides present, and other minerals that could potentially change the color and composition of the scale slightly. So it's a very variable site depending on what part of the property you're on.
Obviously very extreme at this facility.
In order to tackle the problem, we need to find out what these deposits actually were. There was conjecture early on that it was struvite, which is magnesium ammonium phosphate, as Sam mentioned earlier. Or were they calcite, which is also calcium carbonate? Deposit samples were collected from all the scaling wells and analyzed by polarized light microscopy. When we received the results, the samples indicated they were calcite with a trace of quartz present. This was further confirmed by X-ray diffraction, which also indicated quartz and calcite, but predominantly quartz. We also collected water samples to measure the scaling potential using the Langelier index, as Sam discussed earlier, at wells that both had severe deposits and no deposits. Looking at the table, you can see the high pH and high alkalinity at locations 1 and 2, and the corresponding high Langelier index indicating high scaling potential. In contrast, the low Langelier index, where the pH and alkalinity were low, these two wells also never exhibited any deposits. The table also shows some parameters used in the Langelier's calculations. So why were things changing out here all of a sudden over several years? All of the extraction wells were through waste, but only 9 of them have scaling problems. So what is buried here is the question. Looking at historical aerial photos, some of the lakes were filled with crushed concrete. That would explain the high alkalinity and pH at some locations. And if you look at these figures, you can see the lakes on the left and then the comparable location on the right where it's completely filled with concrete. And some of these lakes, is my understanding, are up to 30 feet deep or so filled with crushed concrete. So that can be a pretty dramatic source of various ions associated with concrete.
So Mark, the other areas like on the left-hand side, the green areas between the lakes, was that all MSW waste or is that, virgin ground or what was
That is trash buried in there. And that, we don't attribute the scaling so much to the solid waste deposited there, because if that were the case, we'd have scaling over many more wells than we do. And I'll get into this in a minute about the proximity of our scaling wells and the concrete. This slide shows the most scaling wells at the site. The well to the left, the pH is actually 13 in the groundwater. And these wells are about 20 feet from the concrete-filled lake shown on the aerial. So if you can see that gray mass, that's the concrete-filled lake, and our extraction wells are literally within 20 feet of that lake. Since we tried acid cleaning and jetting with limited success, we embarked on pilot testing some potential proactive technologies to prevent scale. The criteria for success was as follows. It needed to prevent scale on the well screen. It needed to maintain system pressure. It needed to maintain well drawdown and flow rate, and it needed to be cost effective and sustainable. And the figure on the right depicts one of our extraction wells. And the purpose of this depiction is really just to show how this is basically set up across a good portion of the site. We have a well screen, which is below the water table and slightly above the high water table. We have a submersible pump. We have drawdown in the well. We have attempted to use other types of pumps out here. These particular submersible pumps are difficult to remove for maintenance. So we did try using some surface mounted pumps that are easy to maintain and relatively easy to monitor any scale buildup. So we have two different types of pumps at this site. The first pilot test we conducted, we'll call the EM device. Pads were applied to the pump and piping down the well to produce a magnetic field around these features. This testing was performed over the course of 1 year due to scale blockage downstream. When scale was produced on the pump, piping, or well screen, the pads were repositioned and additional pads were later added. A Gauss meter was used to confirm the presence of the magnetic field. It appeared based upon our testing over the 1 year period that the treatment was effective at preventing scale at the pump intake, but the magnetic field radius of influence was not great enough to prevent scale in the well or in the downstream piping. Many more additional pads may have worked, but that option was deemed cost prohibitive. It was our collective opinion that this was not a good fit for this extreme case of scale, so we discontinued the testing. The next pilot test we attempted to use was the electrolytic system, we'll call it that. This was a proprietary technology and the second pilot test conducted. An initial chemical treatment was applied to the extraction well using a weak acid and oxidizer to stabilize the well. A continuous low amperage DC current was applied to an electrolytic flow cell to ultimately change the water chemistry and to modify the charge on the ions that produce scale. Multiple iterations using different metals and multiple flow cells were conducted over the course of a 4-month period. Even after all these iterations, extreme scale deposits continue to appear on the foot valve of the pump and on the well screen. Based upon these results, this technology was deemed ineffective for the extreme conditions of this site, and this testing was also discontinued. The next pilot test involved chemical treatment. We used a conventional scale inhibitor for prevention of scale in heat exchangers or condensers, and it was tested over a 4-month period in a heavily scaling well. The dosage of chemical was based upon the stoichiometry and concentration of scale-producing ions in the groundwater. The results indicated that the scale was not prevented, but the composition of the scale was changed from a hard rock-like material to a soft sandy consistency that could be brushed off relatively easily. The volume of soft material was still great and would still need to be removed from the pump and piping, so this was also deemed unsuccessful. Currently, we are conducting the fourth pilot test, and this is a proprietary chemical formulation. It's a well-specific formulated scale inhibitor, and it's being tested in one of our most challenging wells. This testing began about 2 weeks ago. Preliminary indications are that no scale is formed in the well, pump, or piping after 2 weeks, and all the criteria that I mentioned earlier are being met for pilot studies. SCS will be providing updates on this testing, and the final outcome will be available on our blog.
So Mark, you show a picture of some above ground hose there. Why above ground hose? You kind of referred to that earlier.
Yes, in this particular portion of the site, we have, HDPE piping throughout the entire site, but this particular one is in a section of the property that has a very extreme scaling. This is the area where we're doing our pilot testing right now, and that pipe is plugged solid. We've tried to acid clean that and jet that to no avail. We really don't have enough clean outs in the, I can only imagine the piping must be, hundreds and hundreds of feet with maybe less than an inch of clearance through there. So what we did is we installed this hose as a bypass, and that bypass allows us to also monitor the effectiveness of our pilot test, because we can disconnect sections of this pipe which are connected on 50-foot sections of, with cam locks, and we literally observe the interior of the pipe and see what kind of deposits are present. We can even step on the pipe to see if it's crunchy, if anything's developing there. So this was kind of an alternative to excavating that HDPE and replacing it. So it's worked out really well as far as evaluating some of these technologies.
Yeah, I can see it working at this site because it's a warm climate. A lot of places further north, you wouldn't get away with that. Hey, Brian, kind of boots on the ground perspective, if you will, on that, in need for clean outs. I can tell you from my perspective, it seems like, on the front end of projects, a lot of times, people don't want to spend the capital, and it's like, I don't want more clean outs. We can get this, we can jet from end to end, got 1,000 feet of pipe or whatever with very few clean outs. What are you seeing, and what do you recommend as far as like clean out spacing?
That's exactly what I saw. I like to see about 250 feet per clean out. Makes it a lot easier to troubleshoot, video, inspect, and maintain. It's just works out a lot better that way.
It would be nice to put those in, during the development of the landfill. It's sometimes much more difficult to retrofit that, as we experience that at this particular site, if that's possible. So if this final fourth test that we're testing right now doesn't pan out, we have some additional potential options I'm going to mention. One of them that we've discussed is injection of an inhibited acid such as sulfuric, for example, for pH and alkalinity reduction. Some of the concerns associated with handling an acid like that would be attacking metals in the system, undesirable gas generation from reaction with different types of products that have deposited in the piping, formation of undesirable products directly like gypsum, which is calcium sulfate, potential public access issues, and health and safety concerns. Another candidate study that we've also partially embarked on is relocation of candidate extraction wells to locations with favorable Langler's indices. This particular option would require groundwater modeling to ensure no adverse drawdown effects to sensitive wetlands and still effectively capture the ammonia that we're tasked with doing. As a note, and we have done some preliminary testing of alternative locations already, and some of these look promising based on the groundwater samples we collected for Langler's indices. But in general terms, for this particular site, the farther away we are from the buried concrete, the better.
Thanks, Mark. Hey, we've got a couple of questions up here, and I'm going to maybe ask those. We'll take kind of a quick break here, before we answer these questions before we move in. One of the questions I'm seeing here is, are you seeing benefits further down the line with acid introduction? And I don't know who's best maybe to take that one on. Maybe Sam, your thoughts on that with acid introduction and its benefit as you move down the line.
So acid's going to affect, well, so first of all, I would be very careful about making the decision about that, given the health and safety concerns that Mark mentioned. I've been to the site with Mark, and with public access, with the degree of buildup that occurs in the hoses and the pipe, and the amount of reaction that would occur with the calcium carbonate, because it's an exothermic reaction. There's a lot of foaming and fizzing, and it's a reaction that's going on there. So you have to take all that into account. But like we said, if you're dealing with inorganics, the Langelier saturation index, the first variable there is pH. So lower the pH, the lower the Langelier. There's also the alkalinity. So acid is going to help you out in those situations. And then it also oxidizes organic material also. So there would be an effect, I guess the key thing that you're going to get out of this entire presentation is that every site is different. Every deposition issue is going to take a certain approach that will be probably more successful than other approaches. And acid is definitely one of the approaches.
Okay, I think maybe I'll answer that question. That's great, Sam. It's all good information. I think the question was really more like, when you introduce acid and you're attacking a spot, is it only going to react at that spot down there, or do you see benefits downstream? And my answer to that would be, well, it really depends on the site and how extensive your scaling is, because as you introduce that acid is going to react with that calcium carbonate. It's going to be spent, if you will. It's going to neutralize as it goes through that reaction. So the more, you're going to have to add more chemical to get more effect downstream. But as you clean it and it's not having as much to react with, you will get impacts further downstream potentially before you've seen that acid be spent or neutralized, if you will, to a point where that reaction is not occurring anymore.
Yeah, I'll add to that too. We did an acid cleaning at this particular site, and basically we did like a recirculation loop where we introduced, hydrochloric acid that was inhibited as well. And we would recirculate that back to an above ground tank, and then we'd monitor that pH. And when that pH started approaching 2 or so, then we realized that the acid was coming close to its useful life, and we had to introduce more acid. Until you could really maintain a very low pH, you would need to continuously supplement that to make sure you've neutralized or remove the deposits.
Got another question on here about flow velocity, and does flow velocity affect the scaling? That one, I'll just answer it too. I'd say yes, absolutely. I mean, it does. The more stagnant your water is, the more it sits there, it's easier for those scale crystals to grow. And the more velocity you've got, the more cleansing you can get. Although, depending on how aggressive the scaling is, we've seen even some of those ones. You look at those pipes that Mark showed earlier that got pretty much all the way occluded within a certain amount of time. As that pipe diameter gets smaller, you're number one, you got more heads, you can start to pump less, but you've still got velocity. The velocity is increasing, through those, and it still forms. So there is definitely a relationship between the velocity and the scaling, but at some point, if it's aggressive enough, it really can overcome those velocity parts of it till you shut your pumps down.
And I'll add to that.
Go ahead. I'm sorry, Sam.
Well, I'll add that part of engineering design of piping systems is that velocity component, and so you don't want the pipe to be. I mean, everybody says bigger, better, not so much, not necessarily for pipe sizing. You want it to be right sized so that you have the velocity, but then you're also not restricted. So
I was going to add, it's not a bad idea to do some Langlier's saturation indexes too up front, just to get an idea of what the scaling potential really is, and can you shift that equilibrium by doing something? Because in the case of the study I'm discussing, every well is different. Every composition is slightly different, and the scaling tendency is different at every well. To understand that chemistry, to really understand how to attack it.
Yep. I'm just going to do a couple more real quick, and this one's for you, Mark, on here. One of our participants has asked if there's any cons or what the cons are to the solution that seems to be working. So that'd be the last kind of proprietary chemical.
I think what we're always battling against is also the cost of implementing this. That's something that we're working through right now. We have a concentration that we've tested, and we're now trying to scale that back. We find a concentration that seems to work, but now can we make it work at a lower dosage to make it more affordable? So there's that. I don't see any chemical disadvantage to it. It's proactive versus reactive. Like acid cleaning is reactive. In the particular case that I was talking about, that scale can come back inside of a couple of weeks or so after that acid cleaning. So we really need to do something that's, that prevents it from forming in the first place. But I'd say the only thing right now that we're really working against, even though this site is, this testing is very preliminary at this basis, is what the ultimate cost is going to be to treat each well.
Right now, one of the other questions somebody asked was, was there kind of a cents per gallon or cost per gallon? And I guess I would say at this point, I don't think in this pilot stage where we're at until we get that dosage set up that we're really in a position to where we can say a cents cost per gallon. So I also don't know that that's fair for the vendor for us to just to share that live. So.
Correct. I would agree with that.
All right, I think we better move on here. Next speaker, Mark Pearson, talking about the black goo flubber.
Yes, black goo, it's trouble. We see it in a lot of landfills, certainly one particularly in southern Missouri that we're dealing with. Refer to it as flubber or black goo. It looks a little bit like this guy here, and both of those things are trouble. So we want to get ahead of that. This is what it really looks like. The one on the lower left is the stretchy black goo material we found in the condensate drains in southern Missouri. The one on the right, Brian contributed, force main that completely occluded, and he's shown us photos of stuff that looks like chunks of asphalt or piles of pudding. It comes in lots of different forms, and the places that it shows up and has shown up are places like leachate treatment systems and storage tanks, as well as condensate wells, leachate under drain systems. And so it's a very ubiquitous problem that's and results in costly cleaning cycles as well. So what is this stuff? We took our sample in southern Missouri to the lab and found that it was a majority organic matter, which sort of corresponds to what Sam was discussing about the polysaccharides and the infestation of microorganisms that produce this gelatinous formation that helps to plug up all our piping and under drains. And the methods that have been utilized to remove this material, of course, you can get into if you don't have access to places, it makes it really hard. And if you only have one tank, for example, and it gets clogged up with material, then it's hard to take it offline long enough to get the material out of there, and like a frac tank or an enclosed tank. Furthermore, we have a lot of pipelines that are affected, force mains and such. And certainly you can go in with a jet or a cutter. You may be limited to the reach, and you may have to be cutting in more access points to be able to physically get at it. But the reality is, if this material has grown into your gravel pack under your landfill, you're going to have a very hard time removing that with a mechanical cleaning regimen. Chemically, you can take this, your samples of material to people and see if they can find something that would help attack this and loosen it up. Again, you need access to apply chemicals. You need to be able to recirculate the chemicals, because a one go through, a lot of times the chemicals don't have time to react with the product and to loosen it and then let it go. Every vendor has their secret sauce. So how do you figure out what to do? We took samples of the black goo that was at our Southern Missouri landfill and tried some materials that were on hand as a first order testing regimen. And we had some proprietary material that seemed to liquefy the black goo that we had. We tried low dose hydrogen peroxide, and that seemed to make quite a reaction. And at that dosage, we didn't see a lot of reduction, but we could tell there was something going on there. Simple green we had on the shelf, didn't see much of a reaction. And we had, a cleaning dose of muriatic acid. Again, we saw some reaction there, but our concentrations weren't all that high. But we've seen a lot of municipalities and clients go through sending samples to labs and having them perform testing and come back with proposals based on that, and having a competition that may be economic to begin with, but also to see how efficacious that may be to help come up with a decision.
So what was interesting, Mark, at that site, it seemed like, looking at those samples you had oxidants and acids that work to some extent there. Some of those may be attacking the inorganic. For example, the acids may be more effective at attacking the inorganic than the organic portions, while the oxidants may be the opposite. But I think the point is, that when you get to this kind of like black goo material, it's not just one thing. It's typically a conglomerate of a number of different things, inorganic and organic components and polysaccharides or polymers and all of those things that I know Dr. Benson, who's one of the listening in today on his EREF, study that he's doing, is looking very heavily at that. And maybe a little pitch for him on here too. And we'll send out contact information if you weren't able to see it in the Q&A, but he's really looking for 1 liter sample. So if you have a site where you have this black goo material there, they'd love to talk with you about getting a sample of your material to use as part of their study and looking at what works and doesn't work and how it forms and all those kind of things.
Very important. When it comes to chemical cleaning, if you embark upon a program of cleaning your force mains or your under drain systems with chemicals, it's probably a good idea to have the professionals do that as opposed to trying to provide all the safety measures that are associated with getting your person up to speed. And recognize that you have to employ system thinking to a cleaning protocol. For example, you're going to be releasing a lot of pent up leachate that may be because you can't get it out of your landfill. It's been accumulated. So if you go and get your pipelines clean, now you have this rush of liquid, but now you haven't cleaned out your tanks yet. So you might want to employ some system thinking in that regard. That and material compatibility. You may have valves that have gaskets or seals and pumps and piping materials, maybe air relief valves, for example. It may have materials in it that would be affected by the acids or the hydrogen peroxide or other chemicals that might be utilized. So you might ask your chemical suppliers to take those things into account or proactively replace valves in a cycle so that you're in a better position to routinely perform this kind of activity. Where do you introduce this stuff? You probably have limited spots. You might have clean outs or leachate pumping entrances, access. You have your gas extraction wells and some pumping facilities for your leachate management. These are all opportunities, but you'll need to think about how you get this material in and out of your landfill systems.
I think kind of, proactively, we need to be thinking about that more as we see this, occurring at more and more sites, and this becoming it seemed to be a more common problem. I think we need to definitely be thinking about how, from a chemical standpoint, the clean out standpoint, more clean outs, more access points, those kind of things that provide you options. There's some landfills where you may only have access at one end, to your entire perforated collection system. That makes it very difficult when you're at the downstream end trying to introduce, chemicals to the far end of a line to clean it. It really limits your options.
And the ability to get into the underdrain system. We found that sometimes you have carbonate and non-carbonate materials in your underdrain. And if you dose a lot of acid in there, you may be actually dissolving your underdrain gravel system. So that's something to keep in mind as well. Now you get through all this and you get your system clean, and you find that it's going to be re-emerging, because this is like an infestation that grows and moves within your landfill, we found. So we want to be able to assess why and under what conditions these things are happening. Keep track of your precipitation, temperatures, locations, and a good monitoring system like the one displayed here that keeps track of your leachate levels in the landfill might be a good clue to tell you, hey, things are plugging up. I'm getting a buildup of leachate within my system, or condensate. It's not draining like it should. These kinds of things can help. We're also experimenting with adding chemicals in a low dose fashion to try to keep ahead of things and to see if that's effective. Every landfill is different, and so it's a matter of working together to find solutions to all these conditions. As I indicated, that as they're constructing a new cell here, you can see the perforated drains are only part of an underdrain system. And we need to think about how a chemical might be distributed within the underdrain system to be effective. And, I would suggest that if you're planning on doing improvements or adding a cell, that you discuss this not only with your maintenance people, but also with your chemical cleaning vendors, and they can give you suggestions on how to create a recirculation system that will be effective in keeping your lines clean, and maybe have a method of going to different layers within your landfill to perform monitoring and cleaning activities. So it's really a holistic approach for handling your black goo infestation.
All right, I got a couple of questions I'm going to ask here quick before we move on to our last section here. But somebody asked, have you seen evidence of occlusion on gabion boxes or baskets sitting above the drainage layer material? Can this goo block very large gabion box intakes? So kind of like a window, if you will, down into the leachate drainage layer. I don't know, Brian, is that something that you've seen specifically at any of the sites you're working on?
No, it's nothing that I've seen.
Yeah, I mean, from my perspective, can it happen? Yeah, I mean, I would kind of describe this this black goo material as kind of sneaky, if you will. And it can be in there growing kind of slowly over time, but it sure seems like, it can go undetected for a long time until you have some major problems. You don't know you have the issue until you've got major leachate buildup and leachate coming out somewhere it shouldn't be, or you've got a completely blocked pipe and you notice, hey, I've got no leachate flow out of this cell, which makes no makes no sense. Places like that where it's shown up. But I don't know that. I personally don't have any experience with the gabion baskets and whether or not it's actually formed there that I'm aware of. Anybody else on the panel that's experienced that?
I think that my sense is that a lot of this is happening in areas where there is low flow and where microorganisms are wanting to hang on to something so that they can get to a food source readily. I'm not sure that areas where there's a lot of openings for flow to go through are going to be seeing that kind of blockage.
Yeah, thanks. The other question was more kind of about biocides. And so the things that we've talked about have all kind of been reactive solutions. So once you've got a problem, going out and trying to clear it, and sometimes that's a temporary, hey, going in and, it's ongoing. This question here is more about, does adding DDAC or sort of biocide to the system help prevent the black goo from building up downstream of the introduction area? kind of thinking along the lines of protecting major components only, not the entire system, but in certain areas, specific areas, adding those biocides. Has anybody had any experience with that or tested that yet?
Well, from my past, biocides can be very effective at controlling microbiological growth, obviously. So that's their whole purpose. But specialized biocides are relatively expensive. If you use something more common, I mean, trying to disinfect, then you're talking about applying something to the entire system, which is just loaded with microbiological growth, or the potential for microbiological growth. And then you've got this continuous source. So you really have to look at the cost of the prevention of that. But it's a good approach if you have this, systemic problem that just keeps occurring time and time again, trying to control it. It'd be something to look at. And each situation is different. So it could apply to one and not to another.
All right, thanks, guys. We're gonna go ahead. I've got a couple more questions up here, but I'll answer those. We'll answer those towards the end. I'm gonna go through very quickly here, kind of our last section. In this section, I'm gonna cover on here about a combined kind of organic, inorganic site. It's actually the same site that Mark was talking about, but a different part of the facility. At this facility, they've got a 9-mile, 4-inch HDPE force main that's taking leachate from a lagoon at the landfill to the wastewater treatment plant. That entire 9 miles is dedicated only to the landfill, so there's no interferences or other wastewaters coming into it. After they constructed that force main, it operated great for about 6 years. And then at that point, they started seeing some performance deterioration on it in the form of pressure increases, which were leading to obviously, flow decreases from the pumps out there. Ultimately, it got to the point where they couldn't pump anymore. And that became, crisis mode, if you will. This facility handles about 17 to 20 million gallons of leachate a year. So when they're no longer able to pump it to the wastewater treatment plant, it was kind of an all hands on deck, getting trucking lined up and other ways to manage that, which I know others that manage landfills have been in those kind of situations. It's not a fun place to be. So our initial technical approach was, number one, trying to determine the extent of the problem. When we first started, we didn't know, if we just had a break in the force main somewhere or something got pinched, that area is prone to sinkholes and those kind of things that can, cause, just major structural damage to it. So part of doing that was trying to figure out what we were dealing with. We did some pressure analysis, and we also did some camera and video at select portions where we could, had access to the force main to look at things. Through that, we found out we did have some scale issues there. So we collected samples of that scale. I'll talk a little bit about the leachate and scale sampling that we did and what that showed us. And then obviously trying to solve the problem, get them back up and running as quick as we could. We collected some leachate samples, just kind of looking at that. And we had high TDS dissolved metals, TDS around 3,000 milligrams per liter. Your typical stuff that you see, lots of metals, calcium, iron, magnesium, sodium. Did the Langelier index testing, which showed, we had some scaling potential, but not, it's not super high. It was high, but nothing like what Mark was seeing at the facility he was talking about there, primarily for calcite and siderite. One of the things that was interesting at this landfill, it has both lined and unlined areas. And the leachate that's collected from the unlined areas tends to be quite a bit weaker than from the lined areas, which, is intuitive. There's more stormwater intrusion and those kind of things into that leachate. But as this facility has been built out and more cells are added, obviously the contribution coming from the lined areas is becoming, more and more a larger percentage of the overall generation. You can even see this kind of short term on the graphs that I've got up there, looking at their COD concentrations and ammonia, both are clearly on an upward trend. And we thought, well, maybe this had something to do with, some of the conditions we're seeing and why after 6 years of operation that all of a sudden we're having issues out here. I mentioned us trying to figure out where in the 9 miles we were having our issues. What we did is we had access points. There were some intermediate high points along the force main where we had air relief valves in there. We took those air relief valves off. We installed pressure transducers at each one of those locations that we could link and, and sync up time-wise. And then we would operate the pump at the, at the main pump station and see what kind of pressure response we got. We expected, well, maybe we'll find a blockage somewhere when we don't have any response downstream. And initially we did find that at one location. We were seeing good response, closer to the pump station, didn't see anything. And you can kind of see these spikes on the graph. You see it spike up and then it dropped back down. And then all of a sudden we started seeing pressure response further downstream. Well, that told us we had a clog that was moving. So we initially were stopped by that clog, and then we blew through it somehow with the pressure and kind of moved it downstream, if you will. But I thought that was kind of interesting. We ended up having scale issues kind of throughout. It was definitely more pronounced towards the front end of the force main than the back end. But this approach was kind of one of the ways we were looking at trying to narrow down where the problem was. I mentioned we also use cameras. This is a camera video on the left-hand side. This is showing one of the plugs, if you will, where we had this scale that was sloughing off the walls of the pipe and then accumulating in kind of low points and spots where there's stagnation in the force main. And the right-hand side just shows a little bit closer. The camera was closer to it, and you can kind of see the little chip materials here. And I've got some pictures a little bit later on that I'll show you a little better picture of the scale itself. The scale testing that we did was interesting. We expected initially that we were going to see, typical calcium carbonate scale. In this case, we actually had 40 to 50% iron oxides with some calcium carbonate, and then also organics. I would say this is a good example. What we think is going on. It's a biologically mediated inorganic scale. So it's what we think is happening is that we've got iron reducing bacteria that adhere to the walls of the pipe. They utilize the iron, and as they reduce it, that iron goes from being soluble in the water to being insoluble, and then kind of collects in that biological matrix of the bacteria. And then over time, that kind of hardens on the sides, creates this combined biological and inorganic scale material there that sloughs off when we've got higher velocities in the pipeline. In this case, we looked at doing chemical treatment, but with 9 miles of pipe, that got to be, kind of cost prohibitive. And we were looking at mechanical and jetting. Again, for that much pipe is tough. We ended up landing on pigging, and it's worked very well out there. So pigging, you push these pigs through the pipeline to essentially scrape or scour the stuff off the edges and push it out and remove it from the force main. So we would break the force main up into sections. And when I say break, we would use existing cleanouts or locations where we had access to it. We'd introduce the pig at one end. You use water to essentially push the pig through, and you have a vacuum truck on the back end where you're sucking and removing that material. So eventually your pig will actually show up into that vacuum truck or into your catcher. We had a pig catcher that we designed for this. But in this picture on the left-hand side, you see kind of examples of some pigs that we used out there. The swabs on the left are more of a kind of softer foam material. And we had both 4-inch and 6-inch. This force main again was all 4-inch, but we would actually use the 6-inch larger swabs to get a tighter fit in there, and they worked really well for us. The harder pigs there, scouring pigs, they have abrasives and things on them. They did not work very well in this situation. When you use HDPE and you've got welds, you end up with kind of a little what I would call squeeze out at each one of the joints. So you've got this little lip of material on the inside, so your diameter doesn't stay consistent. And those squeeze outs can be really pronounced when you get to fittings and stuff like, going into, for example, a clean out or a valve or an access location to where, you might have started out with a 4-inch pipe, but you've actually got only 2 inches of open area. We had trouble with those pigs getting caught in those areas. And so we didn't use them very long, I'll put it that way. On the right-hand side, you see one of those used swabs. The squishier, softer ones did a really good job of cleaning, and we didn't have the problems that we had with the hard ones. And that's what we've kind of used from there on out. So these are some pictures of the scale, and this scale forms in very thin layers. So kind of opposed to what Mark was showing with calcium carbonate scale and stuff. This stuff would form in thin layers on the sides and then kind of peel off. I would describe it as looking like cornflakes or little chips of material. And so on the right-hand side, you can see that. And if you look closely, you might even be able to see that it's shaped as the curvature of the pipe. So it was obvious it was coming off the walls of the pipe. But with 9 miles of pipe and you have intermittent pumping, you're not pumping all the time. So, you get something suspended and moving down the pipeline, you're going to shut off for a couple of hours or wait for it to rebound before we start pumping again. That stuff will kind of settle out onto the bottom of the pipe and definitely collect in low areas. And we found then is that we weren't getting a high enough velocity at that point then to resuspend and move that stuff down. And so this stuff would while it was forming kind of all along the pipeline, it would eventually get to points where it would get to low spots where it would build up, kind of cement together a little more, and eventually, create blockages. This stuff is really interesting too with the iron component in it. It would come out black like that, but within a matter of a number of hours, definitely by the next day, that stuff would turn to kind of a red rusty color, as it oxidized. This picture just shows the scale formation on the left-hand side. So you can kind of see the flakiness of it in there on the walls. And then on the right-hand side, that was following a pigging event at that same location. It just showed kind of how effective the pigging was. It was doing a really good job of stripping that stuff off and moving down. We'd have to be careful about how long of a section we would do, because depending on how much is built up, you're pushing all that stuff kind of like a bulldozer in front of that pig, and eventually you will get that pig stuck if you try to go too far with it. So that was kind of a trial and error part of it. There's a lot we can learn from each other, about it. Inorganic, organic, you need to really test your scale specifically, find out what it is, kind of how it's forming, and that leads clues to what's going to be the best approach, chemically or physically, or, however it is to clean it up and get you back and running.
I'd asked, what diameter pipe was that, Nathan, that you were showing a minute ago? And do you have a recommended minimum diameter to really do an effective job with the cleaning and all that?
So that was a 4-inch SDR 17 pipe. We actually had one section near the pump that was SDR 9. That's a little bit obviously smaller ID inside diameter, because obviously the wall gets thicker as your SDR rating goes down. I wouldn't go with less than 4-inch, when it comes to something. If you want to have any real way of accessing it and cleaning it, it's kind of the bare minimum. You're limited, like we were limited to push cameras, in that small by diameter of pipe. So we could only see about a couple 100 feet upstream or downstream of any place we were looking. If you've got a 6-inch pipe, you can use crawler cameras, those kind of things that you can definitely go further to observe more of the piping. In this leachate piping, it's really tough to see anything with a camera if it's full of leachate. Obviously, leachate's typically dark, and you can't see much. So you need to you would have to be in areas where either we'd flushed it with clean water to see it, or where it'd go dry. Because the force main itself here, you'd go up a couple 100 feet from the pump station. And then the general trend of the wastewater treatment plant was down. There were definitely intermediate highs and lows through there, but when the pumping shuts down, a portion of that force main just drains as those air release valves open up and let air into the pipeline, will drain parts of it. That also was maybe part of the scale formation where it would dry out, and that stuff then would kind of die and slough, off the edges of the pipe.
Thanks, Nathan.
You bet. All right. Well, we've got lots of questions up here. It'll take me a minute since I was talking to kind of go through it. Let's start at the top here. One question, is there any indication that this is forming, and this is, I think, in reference to the black goo, at points where the leachate has some exposure to atmosphere, and how far back into the waste does the black goo extend?
Oh, I don't know. Brian, you've seen entire pipelines included.
Yeah, there's nothing to do with atmosphere. I mean, it's black goo. It's all the way from the center of the landfill. I mean, there's just no start or end of it, I guess.
More of an anaerobic type of a material, perhaps?
I would say it's definitely an anaerobic material. And I know, like the Missouri site you were talking about, Mark, that is in gravity lines, both inside the landfill and outside the landfill. We could see with the camera, that we had those issues for a few 100 feet. Again, smaller diameter pipe, we can't get that far. It's hard to see in leachate. You can't really cut off the leachate flow because it is gravity, up through there. But that one is up through in the bottom of the landfill. Brian, you've seen this material in gas extraction wells. You've seen it in, I know just in discussions we've had putting this webinar together, you mentioned seeing it in tanks and all
Tanks,
kinds of places.
H wells, yeah, it comes, straight out from the bottom of the landfill into gas collections, and it has blocked, 8 inch lines solid. In video inspections that I've done, it sometimes sees, force mains above ground. You go into road crossings, sometimes you can see that scale is just, could be a little bit more in the road crossings, maybe where the pipe's cooler than it is exposed to the sun where you have the heat. Yeah, I've seen it, in my tanks and gas collections, force mains.
Question here about what are some of the top suspects for generating the black goo? Are there waste profiles that could be avoided, or rather than avoidance, maybe something could be added at the point of disposal to those waste streams to reduce the potential for black goo to develop? I mean, one of the things, Sam, you mentioned was obviously the polymers, and that's a suspect thing too. I don't know if anybody really knows the answer to this. I think this is the EREF study that's going on is definitely aimed at this. I think trying to come up with why it's forming and where. But anybody else have anything to add to that?
Well, I'll just mention, we're very interested in what EREF does. I mean, EREF does such a phenomenal job with so many things. Very interested in the output that results from that. But we're talking about warm or warmish. You're talking about having a carbon source, talking about dark, you're talking about moist. That's the environment where you're going to have anaerobic in the case of lack of oxygen, or aerobic when you're exposed more at the working phase. You're going to be promoting microbial growth, and there's microbes already present. So it's just creating those conditions like we talked about. And so, that's part of what we're going to be interested in seeing, some finer points regarding those conditions that EREF study hopefully will give.
Somebody's got an interesting question here. Says, anybody let the goo dry out, exposed to air, and find it turn into a gray powder? Goo was pitch black and couldn't be cleaned from a glass-lined leachate tank, but if left overnight, it was a gray deposit you could wipe away. Goo was like black pudding at the bottom of the tank. It was easily removed by suction. Brian, that's something you've seen? You ever seen it turn gray like that, or?
No, I haven't. I mean, I've seen it turn to powder, but over time, if you're using tools to clean up, then it'll flake off. But nothing to say on the ground. We pumped it out and disposed of it, but I haven't seen that.
Yeah, to me, it sounds kind of like an oxidizing event, very similar to kind of what I was talking about with color change you would see with a high iron. I think I would test it and see kind of chemically, what it is, but that sounds like it's oxidizing after it's exposed in there. And then that's why you get the color change and kind of the substance change to it. Again, it's different everywhere because everybody's landfill chemistry is a little bit different. We got commonalities, but everybody takes in different waste streams and has different, climatic conditions and those kind of things.
You were talking about the iron earlier. So yeah, the red, everyone knows about red rust, but there's also oxidation of iron that actually is black or grayish. So you can get different colors with different mixtures of different, obviously different chemical makeups.
I wonder if you could desiccate it somehow, where you take, remove the water from it, what that would do to it, If it was left in the sun, was it because it became dehydrated, turned into a powder?
Yep. Somebody asked, are there special design considerations to keep in mind if you want to use the pigs for cleaning the lines, like recommended sweep bend radii? The answer is that absolutely yes. The more you can, if you think you're going to use that kind of a cleaning method, yes, you want to use long radius turns. That makes it easier. You want to set up so that you can attach a launcher and a catcher, specific locations you want, set up the valves the way you want to do it, and think about definitely, again, having lots of access points to be able to break it up into sections, and where those sections are also locations where, for example, when we're doing this, we're injecting with water. So we're using water to hydrostatically push the pigs through. You got to be able to get a water truck to that location, or you got to have access to that location, be able to do that. Same thing on the opposite end where you can get a vacuum truck there to do it. So there's definitely things to keep in mind if you want to use pigging. And like I said, it's worked very effectively at that site. Unfortunately, we continue to have this problem. So they're having to pig it roughly every 18 to 24 months, but we kind of got it down to a science now. And so the cost of that obviously has come down for doing it. We're definitely looking now at also maybe some chemical methods to where we can keep it from forming. And again, it all comes down to economics, business case equation at the end of the day of is the cost of the chemical offset the cost of cleaning and operational issues and all that kind of stuff as well. Test method. What's the test method for the scale? We've used EMSL laboratories. You can look them up online quite a bit for what's called advanced material analysis. They can do all kinds of different tests. You can call them and talk to them about what you want to do. But the results that Mark put up and showed was some of EMSLs, but they will take a sample of whatever it is you've got, and they will do a number of chemical methods and X-ray diffraction and things like that to look at and identify kind of what it is. Was leachate line continuously flowing? If it was an electromagnetic device tested? I don't know specifically. I'm sorry, I don't know which sites you were talking about on that one. But I would say in general, most of these sites, Mark's site, yes, I think yours does run 20 all the time. The one that Mark Pearson was talking about, that's a gravity line on his. And the one that I had, no, it's intermittent. It'll run, when it needs to. Obviously, we have precipitation events and we've got more leachate in the leachate lagoon, then it will run longer. Otherwise, it does a pretty good job of kind of controlling the levels that we've got, but it's not on continuously.
Yeah, that first pilot test that I discussed was a electromagnetic device that uses pads. And we positioned the pads on the pump and on the piping, and we moved those around and we measured the magnetic field. And it did show some efficacy around the suction of the pump. But this is such an extreme scaling site, it wasn't really as effective as we needed it to be in this case.
Yep. So another question, what was the DO level in the water? I think this one was aimed at the site I was talking about. Considering deposits are mostly deposited iron, increasing the dissolved oxygen might slowly dissolve the iron. Their consideration for that. Actually, we've considered aerating the lagoon itself ahead of time, because one of the things that the form of iron that the iron reducing bacteria use is created in an anaerobic environment. And it doesn't, again, like you said, doesn't last very long if the dissolved oxygen level is increased. So we've actually looked at doing that in the lagoon. Again, it's kind of a cost issue there. It's not inexpensive to aerate. You can do some simple, mechanical aeration type stuff and get some of it. But the idea being, if we can oxidize it in the lagoon, it will again go from being soluble to insoluble, will precipitate and end up, essentially generating sludge in the lagoon that we'd have to clean out there at some point too. But I guess you're moving your problem from one place to another, but it's easier to clean it out of the lagoon than it is to clean it out of the pipe, I would say.
For other leachate applications, typically it's anaerobic conditions at the base of the landfill. So your dissolved oxygen, obviously, until it's exposed to air to oxygen, it's going to be low. So but then regarding that issue of exposure to oxygen dissolving the iron, I'm more familiar with acids dissolving iron as opposed to exposure to oxygen. I'm more familiar with iron oxidizing, which forms a different precipitate as opposed to it dissolving in the presence of low levels of DO in water.
Yep.
Yeah.
Question here, maybe Brian, I think you'd be good to answer. And somebody's asking, can H2S cause scaling in landfill gas wells We have issues with yellow buildup in our wellheads at gas wells with high H2S concentrations.
Sounds like siloxide to me. It builds up, and I have it on a few wells on my site. It's I think it's completely different. The older wells, 15, 20-year-old wells, I don't necessarily see it on my newer wells, but I don't think that has a contributing factor.
Yeah, I'll tell you one, from my perspective, I think, that yellow buildup, it could be slots. And again, you can test these things to figure out what they are. But when you're treating, say, landfill gas or biogas from a digester or something like that to remove H2S from it, one of the methods is biological scrubbing. And when you do that, it forms elemental sulfur in it. And so you have to clean out your biological scrubbers continuously. So I could see certainly in a gas well, if you have the right combination of things, again, it's a more of an aerobic process in this case, but towards the top where you've got exposure to air, if you had the right biology there and you've got an H2S source coming out, you certainly could have that, elemental sulfur buildup there too. So it's possible. Like it could be a variety of things. I think that, let's see, one more on the black goo. If the black goo needs a carbon source, doesn't the HTP liner have carbon in it? If so, is the goo eating the liner?
So the HDPE is an inert. Yeah, there's carbon. Absolutely, carbon is in HDPE, but you need it to be bioavailable, and so the HDPE is not bioavailable. That's why it's used for leachate lines. So the carbon source that we're talking about would be like, some sort of degrading of organic material, like leaf litter or grass or spoiled milk or cotton. And that's actually cellulose, so that wouldn't degrade really either. But it would be a carbon source other than the pipe and other than plastics, which take decades and possibly even a lot of years to degrade.
Yep, like one last question I see here. Are these organic or inorganic components suspended or bound to the water? Does hydrophobic coatings help prevent buildup of scaling and piping and fittings?
So when you look at that Langelier's saturation index at 0, you're basically at the perfect saturation point. Less than 0, it's going towards more corrosive, which would mean that you could actually absorb more calcium into the water. Above 0, then you're moving towards that positive 0.3, where above that you're going to be scaling. So that's sort of my way of referring back to the presentation to show that if you've got higher than that 0.3, then it's not going to be suspended in the water anymore. It's going to be plating or scaling up. If it's less than 0, then it's going to be dissolved in the water, and it's not going to be nearly at the saturation point. So maybe I'm going too far into the weeds on that, but we're talking about dissolved materials, well, like calcium carbonate. Even though it precipitates and forms scale, it can be dissolved in water. That's where it comes from. That's why when you increase the temperature, it comes out in the water tank. That's why if it's in the water tank, but you lower the pH, you can actually remove the calcium carbonate. So it's all a matter of the pH, the alkalinity, the temperature, and the TDS, and the Langelier saturation index variables. Those will help guide it. Google Langelier saturation index, and you'll have hours of entertainment about answers to that question.
All right. Thank you. I don't think I see any additional questions right now on it. I want to thank everybody for your time today. Great discussion. Thank you, panelists, all you guys, for taking part and you kind of sharing what's going on. Like the last slide said, I think we've got a lot to learn from each other on this. It's a common problem that seems to be getting worse, and I know we'll keep working on our end, and anxious to hear what other people are doing as well.
Yep. Thanks for having us.
Yeah, thank you, everybody.
Okay, we're off. Thank you. Bye.
Thank you.
Bye-bye.
Bye.